Okay, so we're talking about advanced input devices. Okay, so one thing that most of you guys got, some of you guys could do better on this topic, is understanding that input devices, sensors, right, go into the top of our device, our PLC, our inputs, I1 through I8. Okay, so theoretically, some of these devices can be used like mechanically, like a temperature that will controller that will, for example, throw a relay that will allow you to directly power something when that temperature sensor goes on and off. Okay, but the way that we use it with a PLC is our PLC is the thing that's doing the outputting, right? Is the thing that's managing whether an output goes on or off, not the sensor itself. Okay, so a couple people, not necessarily saying this is you, but we're wiring sensors into this side of the PLC, which is incorrect conceptually. Okay, so just remember inputs go on the top and outputs come out the bottom for our relays. So we're really focusing on the top part, focusing on digital inputs, analog inputs, and even more advanced sensors that use communication protocols, right? Like we talked about before, I2C, SPI, Modbus, right? To talk literally to our device, okay? So, this is a critical part of process control because it is our eye into the world, right? We are only as good as our data is. We are only as good as our sensor is, okay? So if our sensor has noise and inaccuracies, then so will our output, because we can't tell the difference between error or noise and the thing that's actually coming from our signal, from our sensor, okay? In general, sensor is a very broad concept. The more specific concept is this idea of a transducer. Okay, it's a very cleverly designed material that will turn one physical phenomena into another, right? There's many different kinds of transducers. You can have electricity into many different things, electricity to sound, to light, to pressure, right? All of that is a transduction, and it's done with a transducer. Okay, there are many different kinds of other things, but in our realm, we are really just focused on clever ways to turn electricity into other physical properties or other physical properties into electricity and be able to measure the quantity of that thing. Okay, so at the end of the day, someone has to design this thing, right? Someone had to make the first sensor of any given type of thing. Okay, so they had to decide what makes a good sensor or what makes this better than another way. The things that make a good sensor is high signal to noise ratio. Again, the signal that we're interested in isn't buried in other noise that we're not interested in. Okay, reliable output. If we have a temperature sensor, it's not a great sensor if it varies widely with pressure, right? If the weather changes on that day and the ambient temperature of the air pressure changes, then our temperature value is now useless, right? Unless it's held at precise pressure or whatever. So a good sensor doesn't care about what altitude you're at, doesn't care about where you are in the earth, the ambient temperature. All of these things are controlled or otherwise mitigated in its design. It's tough to do. And it also responds to little outside of the phenomenon of interest, right? A lot of times this comes up in gas sensors, right? If we have a gas sensor, we're trying to see the concentration of carbon dioxide in a tank. Okay, but if that output of that sensor also changed with the presence of oxygen, right, for whatever reason, we couldn't tell the difference if oxygen was leaking into our tank or if we were detecting the correct amount of CO2, right? All of these things are important and matter. The output of a transducer, like I said, can take many different forms, but in the end of the day, we have a signal in a can, right, in our device that we need to get out of that can and into our PLC. And it goes, how do we do that? How many wires do we take to do that? How long can the signal integrity go before we can't read the signal anymore? All that good stuff. So that's where typically the sensor designer will go, okay, how do I want this sensor to talk to the world? What does it make sense to talk? Is it a light sensor that might just want to say 0 to 100% light and have the analog resolution output to go those steps? Is it a beam break and we just need on-off, like high voltage, high reliability on-off signaling? Okay, all that stuff is taken into account. We talk about analog sensing much in this class, right? We touched on it, I think, right? Did we actually talk much about how it works? No? Okay. All right, cool. What's that?
I think we talked a little bit about the range of voltage. You can make it to certain things.
Gotcha. Gotcha. Yes, so there are many different kinds. This is called an analog to digital conversion, or an analog to digital converter. There's different techniques called sampling a signal in order to digitize it, right? So this is taking for example, if we have an analog temperature sensor, we could infinitely digitize that sensor to any resolution between our min temp and our max temp, right? We can separate that into as many different bins as we care to, right? That makes sense to us, okay? Typically, this is binned into either 0 to 255 bins, so 255 different dashes, right? That it takes a really smooth signal like this, and it kind of chops it up into something that looks a little more digital like this, right? Because it only has so many discrete levels to change at, right, according to the sampling rate. It's a little ugly at the end there. But you guys get what I'm going for, right? Okay, so this is the analog resolution. Okay, typically from 0 to 255, or 0 to 65535. Because again, this is an 8-bit number, which means we just have 8 zeros. And then if you have 8 more zeros, you can represent a larger number. If you have 16 zeros or 16 ones, this is the maximum number. It's 2 to the 16 is 65535 if you punch it in the calculator. Okay. So, what our device does is it essentially has an internal comparator that it could tell each of these bins and the voltage that this bin is at, and it compares it to an internal reference. And it says, am I above or below this bin? And it says yes or no. And then it says no, am I above or below this bin? Yes or no. This is a specific kind of analog to digital converter that I'm talking about. It's called fly sampled. Okay, again, this is getting into the weeds of it. This is more than you guys need to know. But all we're saying is that we're taking a signal that can vary widely, that we can, again, so this signal is some voltage, right? Let's say 0 to 5 volts, okay? So 255, if we read on a multimeter, would read 5.0000 volts in an ideal world, right? 125, right, half of 255 would read approximately 2.50000 volts, right, on a multimeter, half of our range. Okay, with me so far? I see a nodding heads, this is good. All right, so the next thing that I wanted to say about that, point that I was building to. All right, in any case, we only need to talk about turning, oh right, sorry. Okay, so what I was saying is that this actual signal, okay, like if we zoomed in on it in the real world and took an actual multimeter to it and like monitored it in real time, okay, we could digitize that signal and not bin it to, 2.500 volts, because that's like plus or minus, some 0.2 volts for that bin, right? There's some sloppiness in the bin. If it's anywhere a little bit higher than that or a little bit lower than that, it'll just read as 2.5 volts, okay? But if we looked at the signal itself, we could digitize that signal infinitely to 2.50284796, you know, blah, 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 to like really specifically digitize that signal. But we don't really care, right? We just kind of care that this gives us some appropriate resolution, that 255 bins is enough for like, you know, 1 degree per Celsius change, or like 1 bit is what we call it. The difference between one of these bits flipping is that significant. And if it is, like, that's all you really care about. And then for really things like audio, right, is really where you need that higher bit depth. So this is where you see like 12-bit, 14-bit, 16-bit, 24-bit, right? That's like audio, like crazy high reproduction quality. Not really so much in our sensors. So that went a little bit longer than I thought. Sorry about that. But does that explain analog to digital converters just a little bit? Okay. So that's good. All of this here to talk about different ways that things can talk to our device. Okay. So before I said, how do we actually like wire it into our PLC? Right. Rubber meets the road. How do we do this on our PLC? The cool thing is, if we have a wire that contains our analog signal, which is to say if we put a multimeter on that wire, we would see it vary with whatever property we're looking to see, light, temperature, whatever, right? If we put that into one of our inputs on our PLC and then told the program this is an analog input, we would see this number in our code, 0 to whatever resolution we set it. It's actually a drop down. You could set it to 8 bits and it would give you 0 to 255, or it would give you 12 bits or 16 bits and it would give you this number. And then in your code, you could do things like, if the number is greater than this other number, do the thing. If it's less than that number, do the thing. And that's how you can use the sensor for analog sensing. Okay? Okay?
Instead of saying if whatever is true or false, will we use those numbers then?
Right, it would yield, you would go like equals something, you would store it in a variable, it would store that number, and then you could do whatever you wanted to do. You could even convert that number to like a temperature with a simple math function. Maybe one line of your program just multiplies it by a constant, and now you're working in Celsius, and then it's nice and easy. Okay, so that brings me to a really effective sensor that comes up all the time, the Hall effect sensor. Okay, that's some vocabulary for you, the Hall effect sensor. Okay, it effectively is a digital magnet sensor. Okay, it allows us to, there's actually different kinds of this sensor. It looks just like this, almost like a little tiny transistor package. Okay, and the output of that sensor, one of these 3 pins, one's power, one's ground, and one's data. That data pin can either be on, off, there is a magnet or there isn't a magnet, you know, close to some threshold, where past that threshold it'll turn on. Or it'll give an analog output where it'll actually give you, you know, how much magnetism is nearby the sensor at a given time on that data pin, right? And then maybe if my sensor's right here and my magnet is right here, this distance would read as 255, and then there would be some minimum distance all the way out here that you would move the sensor and barely be able to detect it, where you're starting to get like 2 to 3 coming in on that pin. And it would change, the number would change in real time. Still with me? Cool. So Hall effect sensors are just all over the place. One really good example of it is in bike pedal detection. So bike pedal detection, the way that bikes can tell if you're pedaling or not is there's actually just a captive magnet inside of the bike pedal, and then there's one of these sensors that's mounted to the frame. And then every time the sensor passes the magnet, or the magnet passes the sensor, we get a pattern that looks exactly like this. Blip, blip, blip. And then you could either, you know, set a threshold and detect when it goes over the threshold. There's special algorithms to detect blips. You know, you can do whatever with that signal in order to actually do what you want to do with it. Okay, but a lot of the trick is that these sensors just give us this one-dimensional data. You know, we can see, is it high or low, or how high is it in the case of analog data, but it's up to us to like assign behavior and output and meaning to that data that we see. It's just a number that we have to deal with otherwise. Yeah? Cool. All right, so thinking we're doing good. Now I'm just going to go through some different kinds of sensors, just kind of buckshot, give you guys some quick experience. We've already gone through Hall effect sensors, magnetic sensing, okay, but now we're going to go through some capacitive sensing, some inductive sensing, things like that, okay? So, first up is a capacitive sensor. We won't actually spend too much time on this, but I would love for you guys to kind of start to understand the electrical concepts behind this, right? Like, how does a capacitor work, and why would we use a capacitive sensor rather than something else, for example? Okay, so this slide in particular, it's very easy, very easy to take a voltage output from a sensor, right? Is we just kind of like I said, if we put a multimeter on it, we can see a voltage. It's just kind of there and readable. Our instrumentation won't change that voltage significantly by like touching it with our probe, things like that. It's fairly stable. But a lot of our transducers, right, the physical property that's changing in our chemistry, whatever, in order to change that into a voltage, we need to do something to it. It's not just readily available as a wire that has a voltage on it that we can read right away. We need to condition it first. Okay, so that's kind of where this starts to come in, and how we can read other different, or I guess like raw transducers that turn these physical properties into voltage, which is ultimately what we want to read, right? So the first thing, probably the simplest example, is a change in resistance. So if we have a device such as a thermistor, okay, it's literally a resistor. It looks like any other resistor you've ever seen, okay? Well, actually, in real life, they don't. They look like glass beads, like this, with beads sticking out of them. That's what they actually look like. But on paper, they look like resistors, okay? So what happens with this resistor is if we put a flame to it, okay, and again, if we read this with a probe, with a multimeter, we would see the resistance of this device change, okay? We could inherently kind of understand why that's useful, right? Change in resistance with a change in temperature, if that's a linear change, that's a darn good sensor right there. But the issue is, how do we get that into voltage, something that our PLC can actually read, okay? So we use a technique called a resistive divider, or potential divider, okay? So an interesting thing happens when you put one resistor that changes, this is a variable resistor, on top of one resistor that doesn't. You kind of make a balance beam that swings. Okay, so this part is powered, for example, 3.3V. We are looking at this with our multimeter. So this is the spot in between our changing resistor and our not changing resistor. And then the nominal resistance of this thermistor is 10K. Okay, in a 25-degree C room, it measures as 10,000 ohms. If we put it in a really hot room, it would either go more or less depending on a coefficient that can actually either be positive or negative depending on the particular thermistor. All that to say that the literal resistance of this will change, okay? Now, the ratio between this one and this one will define the voltage at this point. If they're exactly the same, our voltage will be exactly half of our source voltage. We always know what this voltage is, okay? And you guys might be able to see that as this resistor either grows or shrinks, it will shift our point. The ratio will change, and thus the voltage will change. So this won't be, 1.65 volts anymore. It will be either more or less, and that becomes our voltage signal, okay? So pretty cool, pretty easy, very cheap, right? 2 resistors is like cents, okay? You can't really power much with it because this is 20 kiloohms of energy, right? But as long as your sensing device doesn't suck too much amperage out of this, doesn't disturb the circuit too much, you can sense away from that, okay? So that is a potential divider, extremely good technique to know, okay? All right. I'm not going to go into capacitance too much. One thing to know is that it's actually how our phone screens work. So I'm going to actually tell you how this works. So if you imagine a bucket, okay, and we are filling that bucket with water at a very defined rate, okay? We're also leaking water out of that bucket at a really defined rate, okay? So now, if we check up on this bucket, if we continually open and close this latch so that we rise and drain this bucket, we'll kind of make waves just like this. Okay, you guys with me so far? Okay. Now, imagine there was some property that this size of this bucket changed with the weather, changed with some property. Okay, so now we have a slightly larger bucket. Okay, we're still filling it the same rate, still emptying it the same rate when we open the latch, okay, but the dynamics are a little bit different. The water is now slightly higher on average in our bin, okay? This is the idea of changing capacitance, okay? Remember, the idea of capacitance is how much electrons we can temporarily force into something, okay? So if something can temporarily accept more electrons or temporarily accept less electrons, this means it has more or less capacitance. Yeah, still with me so far? Okay, so changing capacitance is kind of like changing the size of this bucket, okay? And we can tell the capacitance of this bucket not by measuring it directly, but by telling how much is in this bucket at any given time. If we change the level of this water fast enough and look at where the average level is, okay, if it's here or if it's a little bit lower, if it's here, that's how we can indirectly measure capacitance and tell if capacitance is changing. This voltage, or sorry, this signal, I just spoiled it, is voltage, okay? So this is a quick analogy, hopefully didn't throw you too much. How we do it electrically, okay, is that we have a capacitor, we have that has one leg that is charged, right, that is attached to, we can actually control it with a microcontroller. Okay, so we can charge this pin or not, and then the other side just slowly leaks out like that, okay? So now, pretend like I touch this object. That increases the capacitance of it, right? The union of my hand, the increased surface area of my body increases the capacitance of this, okay? Now, what we do in real life is we really rapidly charge and discharge this capacitor, like thousands of times per second, okay? That will cause the voltage to float something like this, okay? And if we were to touch it, if we were to do something to change that capacitance, then that would immediately change the voltage, just like that, okay? So that's what I'm describing here, okay? There's another idea. I'm going to come at this mathematically, because what I'm also describing here came up in your other classes, whether you knew it or not. You guys remember tau, the RC time constant? Raise your hand if you ever heard the term time constant before in tau. Okay. All right. This is actually really worth knowing. I wish more of you guys knew, so I'm going to pull it up. This is a really critical concept to know. Here we go.
Meta, how can I get my 2-year-old his breakfast?
He likes it when you make silly faces.
Let's say we have a 9-volt battery, a 100 microfarad capacitor, a 10 kilo ohm resistor, and a switch, which are all in series. The capacitor is fully discharged, and we read 0 volts across the 2 leads. When we close the switch, the capacitor will charge. The voltage will increase until it is the same level as the battery. The voltage increase is not instant. It will have an exponential curve. At first, the voltage increases rapidly, and then it slows down until it reaches the same voltage level as the battery. We split this curve into 6 segments, but we're only interested in the first 5, because at the 5th marker, we're basically at full voltage, so we can ignore anything past this. Each segment represents something called a time constant. Therefore, as we have 5 segments, we have 5 time constants. So, it will take 5 time constants to charge the capacitor from 0 to just under 100%. All we need to do is to calculate how long one time constant is, and then we multiply this by 5. To calculate the time constant, we use this formula. Time constant in seconds equals the resistance in ohms multiplied by the capacity in farads. So we convert our resistor to ohms and our capacitor value to farads, and we see that 10,000 ohms multiplied by 0.0001 farads equals 1. So in this example, the time constant is equal to 1 second. Therefore, 5 of these is 5 seconds, meaning it takes 5 seconds for the capacitor to fully charge to 9 volts. If the resistor was just 1000 ohms, the time constant would be 0.1 seconds, so it would take 0.5 seconds to reach 9 volts. If the capacitor was 1000 microfarads, it would take 50 seconds in total. So, as the capacitor size increases, the time taken will also increase. If the resistor value increases, then the time taken also increases. Coming back to our original circuit, we can therefore calculate the voltage level at each time constant. At point 1, the voltage is always 63.2%. Point 2 is 86.5%. Point 3 is 95%. Point 4 is 98.2%, and point 5 is 99.3%. So the voltage will never actually reach 100%. That's also why we stop at just 5 points. So in this example, after 1 second, the capacitor...
All right, well, not to get caught up in the math too much, I'm going to see if we come back around. Yes.
We could also... The current of the circuit decreases while the voltage of the capacitor increases.
Okay, so here is another way to explain this. Okay, just one more, and then we'll move on to inductance. Okay. All right, so imagine, again, that we have a capacitor, and we are charging that capacitor. It's like we have just a bare capacitor, and we attach a lead to it, and we're charging it, okay? That capacitor will charge up to our maximum voltage in a curve that kind of looks like this. And this is, you know, our source supply, 3.3 volts, whatever, okay? Imagine if we checked up on it at some point that we knew it wasn't charged yet. Like, always knew it was still in the recharging curve, okay? So here, this might be like 0.25 volts. Okay. Now this is a capacitor of this size. It's a bin of this size, again, that we're filling with water only so fast. Okay, so a bin of this size that we're filling this fast would have a water level of here. This is our voltage, the pressure that's being given by our capacitor. Okay. If we had a larger capacitor, larger bin, we are still filling it with the same amount of water for the same amount of time, but it will charge much less slowly. The pressure will gain much less slowly at the same time that we check in on it again, right? It's a bigger tank. The same amount of water will fill much less space, will exert much less pressure. Okay, fundamentally how a capacitor works, okay? So again, this is how we can, by charging a capacitor, emptying it, and continually charging it again and seeing how charged it gets at a specific point and doing that really, really quickly, again, like tens of times a second, hundreds of times a second, we can see the capacitance of something because we'll see that voltage rise and fall, okay? So how this all relates to smartphones, okay, how it relates to our daily world, is that capacitive sensors are very often used for touch sensing. Again, because if you change the surface area of something, if you change how much contact or like availability of surface that electrons have to jump to, you will change the capacitance of something. Excellent for touch. Okay, when two objects meet, the amount of surface area that's available for electrons to jump to is much greater. Okay? So what happens in a cell phone is that it separates your screen into 1,000 little capacitors. Okay? And then each and every one of those capacitors, it will charge it and then check in to see what voltage it's at, right? 0.25 volts. Okay? And then charge it, discharge, charge it, discharge, charge it, discharge. And if you have a finger there, okay, when it charges it, it might come at like 0.35 volts. And it goes, ding, I have a finger here. Touch registration. Okay? Get all those touch registration points together. You know, you might have like a few that all register here. The software says, I register a touch there, and it passes it to the operating system. Okay? So a capacitive array, a capacitive touch sensor. Okay? Interestingly enough, you can also have resistive touch sensors. Okay, in that case, the Nintendo DS, for example, used resistive touch sensing, while the Switch uses capacitive sensing. Resistive touch sensors had that like gummy gel-like screen. Okay, the way that those worked is they actually had two wires, one overlaid like this, one overlaid like this, and when you push down on them, the pressure met. And it could tell which two unions you saw because the resistance of this line and the resistance of this line would drop. And again, it would scan through and figure out where you touched. Sensors, same thing, right? Touch sensing of a screen, but completely different technology in the way that it goes into the computer. Any questions on that?
A lot of data to process.
Oh yeah, yeah, big array for sure, and many times a second too. So inside of your phone, there's a little chip that's dedicated to doing this scanning and capacitive sensing, and like that's all it does. It lives and breathes is to just figure out where on your phone you touch the screen, and to charge the cells and do all that. Any other questions? Keep moving. All right. So I'm not actually going to go through inductive sensing, although it's somewhat similar. Things you should know about inductive sensing is that it's often used for proximity sensing of metals. Okay, so capacitance sensing, resistive sensing, extremely high accuracy probes are often inductive sensors for metal sensing. It's kind of like my phone. Already talked about capacitance. All right, now we're going to go through pretty much like the quintessential sensors that I think every person should know. Okay, so like I said, more good vocabulary for you. Okay, how a button works. First one, simplest one, possibly the oldest one. It's called a reed switch. You guys might not have encountered this, but you've definitely seen them before. This is what windowsill security systems use. You ever see those two halves of a clamshell that's on a window, and when they separate, you know, the window comes apart? So the way that that works is that there's actually a glass cylinder on the inside. There's two wires going off here and going over here, and then they overlap with two tiny metallic filaments almost. Okay, they're magnetic, so in the presence of a magnet, they'll snap together and create the connection. So the two wires meet and create a switch, essentially. You made a magnetic sensitive switch. So used all the time in older technologies, these reed switches, because they're fairly reliable, really easy for doing logic with, knowing when things are in certain positions, right? If you slide thing in position A or position B, that will throw two relays together, or sorry, two reed switches, which will do things, okay? Limit switches look like this. Again, something you've probably seen before but didn't know the name for. Okay, this is a limit switch. It's often used for position sensing of robotics. Okay, some robots don't actually know where they are in the world, so they'll reset against a known point. They'll bump against a switch that looks just like this, and when it triggers that switch, it knows exactly where it is in space, at least until it loses its spot again. It keeps doing what it needs to do. So this is why 3D printers home themselves, for example. If you guys have ever seen that happen, when it first starts up, it slams all the axes into one spot, so it knows exactly where it is and it moves relative to that point again. So often used for safety features. Okay, if things bump into these switches, it will often turn off the device or cut power or keep a motor from moving in that direction, hence the term limit switch, right? It will actually like physically cut off power in that direction so the motor can only move in the other direction. So we talked about this before, but it's worth dialing in on because a lot of people, again, don't really realize how complicated the devices we work with in our world are, right? It's easy to take, well, not advantage, but to think little of the humble button. But at the end of the day, it really is just, this is the leg of the button right here, right, that goes into our breadboard or whatever. Just a strip of metal. This part deforms, so this is the force that resists you. This is where you get the click from. It's just a dome that faces up that when you push down on it, caves in. It makes the click, it makes the contact between these 2 points. And then by changing the thickness of this material, you can get different forces of buttons, ones that click or ones that will just, gently cave, things like that. And it just couples. This is called a galvanic connection. Okay, there's another vocabulary term for you. Metal on metal contact is a galvanic connection. Okay. Here's our light dependent resistor. This is often used in security systems, right? Lights that come on at dusk and things like that will have these sensors in them. So this is an excellent example of a resistive device. Okay, just like we had a thermistor before, which was our little glass ampule that if we heated it up, the resistance would change. This one changes with light. If you put it in the sun, the resistance changes. If you put it in the shade, the resistance changes. Okay, it's kind of cool. But so by putting this in a divider, right, pairing it with another resistor, we can get a voltage out of it and use it as a sensing device. Really cheap, really effective. Talking about cheap and effective, this is a mercury switch. Very clever device. Again, it's literally just a glass ampule with a bit of liquid metal inside. When it's in a very certain position, either upright or over or however the designer wishes, it will connect these two wires. Okay, this is often in space heaters. For example, if you knock it over and you hear the click, it's because the ball came out of contact and turned off the heater until you turn it upright again and it restores operation. This one, really useful to know, is called a quadrature encoder or an AB encoder. Okay, not going to get too much into this one. Again, just laying the vocabulary out for you guys. Each one of these is a short or a TikTok or a video, right? That they're all cool and interesting, all very useful, all ubiquitous in our world. It's very common. Okay, so the way that these work is, and why they're useful. So this is a motor encoder. This allows us to see the movement of a motor. Okay, very often we just tell a motor to move and we don't know how much it moves. It's really useful to see, how much it moves, how fast it moves, the acceleration, all that stuff. So the way that we keep tabs on a motor is we have our motor can right? That motor will have a spindle on it, that spindle is spinning, and then often on the back of it, attached to that same spindle that's just sticking through, right, is our little encoder. And this sensor will ride on the back here and give us some rotational information about the motor. And it can do that in different ways, okay? Some encoders, okay, if I'm looking at that data line, they'll just blip a lot like our Hall effect sensor before, right? And so each blip means that the motor turned one rotation, okay? So that's pretty useful. We can get speed that way, right? Count the blips per second and we have revolutions per second. What if we want to know whether it's turning forwards or backwards, okay? The way that we do that is we add another line, okay? And if we see that this line blips slightly before this line, it's turning in one direction, and if it blips slightly after, it's turning in the other direction. That's really all it is. That's the cleverness of the quadrature encoder. So here, it's not blips, it's square waves, but you see that here, when we are turning counterclockwise or clockwise, the A line blips first, right, slightly before the B line. But here, when it's turning the other direction, B blips first. Okay, you can do real simple code. If A blips before B or whatever, you're moving in one direction, you're moving in the other direction, you can see the speed of both. Really clever, really useful. Okay, so this is an A-B quadrature encoder. And then the different qualities of encoders, like some of them will blip, you know, like 1,000 times per resolution. You can get really tiny granular movements out of it. Some are only like a dozen, you know, little toys for things like that. You can have optical encoders or electrical encoders, all that stuff. This is another similar one used for input, right? Turning, you know, through a menu or something, clicking through a menu. You can do the same thing. If you've ever had a dial that you can turn forever in one direction or the other and it clicks, it has indexes, that is also an example of a possibly blipping encoder just like this. And all the device sees is pulses in one direction, so it knows you're turning to the right or to the left. And you can work it out from there. Very important device, potentiometer. Comes up in almost every class. It's a pretty useful thing to know. Okay, a potentiometer is a mechanical device. If you don't know how it works, essentially the way that it works is if we have a long strip of resistive material, think like graphite, right? Something that's conductive but not extremely well. Okay, if we put this side on ground and we charge this side, say like 3.3 volts, and if I put a multimeter right along here, oops, bad multimeter probe. Anyway, I put my multimeter along here, and if I slid it down all the way from this end, I would read 3.3 volts, and go all the way down here, I would read 0 volts. Okay, that's kind of the beauty of the potentiometer, in that it is itself a resistive divider if I put it in this orientation, in this wiring. Okay, so imagine if I charged this side, grounded this side, and sensed this part. Right, you can see that it makes a divider that changes ratio from this side of material to this side, how much material is on either side. Okay, and that gives us a changing voltage, right? 0.00 volts that we can go into our device. So potentiometers, volume knobs are very, very often potentiometers, right? Dials that have a distinct end to them, left and right. You can turn them all the way up or all the way down. Slides that you can move all the way down or all the way up, very often potentiometers, okay, the thing that you're actually interacting with. Sometimes you see these little ones, these are called trim pots. Like settings for things are often set with trim potentiometers. You're just changing the resistance that sets, like, you know, the current of a motor or the volume of a speaker or whatever. You're just changing the resistance of an element. Okay. All right, we'll take a break in a little bit. This is a lot of information. But I'll end for right here, or at least, you know, before we take a break, on our humble float switch. Okay. So float switch is an extremely common industrial device because we really are concerned about the level of things in tanks, right? Like water in a tank or something like that. So often you will have a magnet suspended in a floating piece of plastic or a balloon or something like that. And then you have a part that's fixed to the tank or the container or whatever, so that when buoyancy will affect that floating part, it will bring a magnet closer to our magnetic sensor. And that sensor can be inductive or a Hall effect sensor or whatever, right? We register that change. That's a float switch. It's called. So this one was a bit of a freebie. I actually already went over this one, but this shows you what it actually looks like in practice. Okay, so again, all these bead types are thermistors, which means that if I measured the resistance of this, it would come up to some resistance at room temperature, like 10K. And if I held my fingers around it and brought it up to, the approximately 100 degrees that our body shows, the resistance would change as you read it on the meter. And then you would typically put this into an amplifier or some small device that would, let you read that out as, temperature in degrees C or degrees F. All right, the next one we're going to get into MEMS, which is manufacturing technology for accelerometers. Cool stuff, but a little involved. So we're going to take a break. I'll give you guys about 5 minutes. We'll be back at 6:56. Keep going. All right.
What was that acronym you said, manufacturing?
MEMS, yeah, MEMS. Should be micro electromechanical systems.